All right. Last time we looked at molecules like this. This is a hydrogen molecule. And what did we say that that line in the middle represents?
Shared electrons.
Yeah, and specifically how many?
Two.
Two shared electrons. Would you expect in a molecule like hydrogen, would those electrons be shared evenly or would they be shared unevenly? Would you say? Evenly. Why? You're right. Why? Yeah, I mean, there's some symmetry here, right? You've got a hydrogen on one side, a hydrogen on the other side. So why would the electrons go more on one side than the other side? And so you're right, they don't. They basically get shared evenly. But if we look at something like this, now remember, these other extra electrons are not shared. Those are the unshared electrons. But those two electrons in that bond are also actually not shared evenly. Any idea why that might be?
Because of the charge of the electrons, they push each other away.
Well, the electrons can push each other away, but why would they both then go to one side versus the other side?
Is more negative.
Kind of, yeah. There's a quantity that we're going to look at now that is called, or a property, it's called electronegativity. Have you ever heard that word before? Maybe not. I don't know. I don't know if you have or not. It's an important word in chemistry, and it means the ability of an atom to attract electrons in a covalent bond. So we're not talking about just like the atom is out there and electrons from other places are magically attracted to it. That's something different. This is saying when we have a bond, and a bond is always between two atoms, one of them can pull the electrons more than the other. And the one that can pull the electrons more than the other is said to have a greater electronegativity. So let's look at what those numbers actually look like. We'll pull a picture from the book because it's a convenient table. It's on page 189. So here's a table of electronegativities of some elements. The metals are in the middle are kind of left out because those mostly just do ionic bonding, as do most of those other metals, but you can see their electronegativities are quite low. Generally, when we talk about this, we're talking about it in the context of the non-metals because we're talking about covalent bonds. So if you look over, you see a variety of numbers like 2, 2.5, 3, up to 4. And you don't need to memorize any of these numbers, but what you should know are these general trends. We can look at the periodic table and we can make a reasonable guess as to whether one atom will be more electronegative or less electronegative than another based on where those things are. So if you can't read that well, I know it's a little dark. It says electronegativity increases as you go to the right and decreases as you go down. Another way to think about this, the way I think about it, is that the most electronegative element is fluorine. So another way you can think about the trend is everything goes toward fluorine. Higher electronegativity is the closer you are to fluorine. That mostly works. The reason you'll notice in some cases it's really hard to compare. So if you compared, let's say, nitrogen and oxygen, you would say, oh, well, oxygen is on the right of nitrogen, so that means it's closer to fluorine, so that means its electronegativity should be higher. And if you look at the numbers, it is. See that? The other way you could do it is up and down. Oh, between nitrogen and phosphorus, nitrogen is higher than phosphorus, so therefore nitrogen should have the greater electronegativity. In that case, it's not so much which one's closer to fluorine, but the trend still goes up to where fluorine is, if you look just in the... Sometimes it's not so easy to tell. Let's look at nitrogen and sulfur. Nitrogen is higher up on the table, but sulfur is further to the right. So we can't really make that comparison unless we have the numbers. There's no way we can just kind of look at the table and say, oh, well, that one should be higher. So when I ask you to make these kinds of comparisons, I would generally do it in a way that is clearer, either left to right or up and down, so that you can actually make that distinction. Does that kind of make sense? Mm-hmm. All right, so we're going to look at some bonds this way. And first, we're going to talk about what that actually means for the bond. So we said that this HF bond, the electrons were not shared evenly. So which of those two atoms would you expect to pull the electrons more? H or F? F, because that's got the higher electronegativity. So fluorine with its higher electronegativity of 4.0 and hydrogen with its lower electronegativity of 2.1 says that that these two electrons in this bond are actually kind of more around the fluorine. If we look just at those two electrons, wherever they happen to be, as they're going around, they would be kind of more over toward the fluorine side than toward the hydrogen side. And the net effect of this is that the electronics are no longer even. We no longer have a totally neutral situation because the electrons are lopsided, and electrons have what kind of a charge? Negative. So if your negative charged things are spending more time over here, then this side is going to be more negative than the other side. You see how that might work? So that tells us that, I'll redraw it here, that in the HF molecule, there's going to be kind of more negative over here by the fluorine, and there's going to be more positive over here by the hydrogen. It doesn't mean that it's ionic. It doesn't mean that we have a full charge because hydrogen's missing an electron or fluorine's gaining an electron. It's not like that. It's just that the electrons are spending more time over on the fluorine side, making it a little bit more negative. We have a symbol for that. It's a Greek letter, delta. We make a delta minus where it's more minus. We make a delta plus where it's more positive. And so this tells us there's kind of a little bit of a difference there, and a little bit more different, a little bit positive on one side and a little bit negative on the other side. We refer to this as a partial charge. So it's not a full charge like an ion. It's a partial charge. It's a little bit of separation, kind of in between. If you have a bond with that situation, then we call that bond polar. A polar bond, just like a north pole and a south pole, means that it's separated into two poles, a positive and a negative, through these partial charges. So we would call that charge, we would call that a polar covalent bond. The hydrogen one up here, since those would be the same, we would call a nonpolar covalent bond. So you have polar and nonpolar. And you can determine whether a bond will be polar or nonpolar based on whether or not there's a significant difference in electronegativity. What this kind of turns into then is that there's actually variations in bonding across the whole range from purely covalent to purely ionic. That it's not exactly two categories, covalent and ionic. It's like covalent, ionic, and then all this polar stuff in the middle. And the book gives a general guideline to that, as well as some slightly nicer pictures than I drew. I don't know if you want to check that out, but you see here, depending on how big the difference in the electronegativity between the two atoms is, if there's no difference, that's purely nonpolar, and the electrons are shared equally, kind of like this. If there's a huge difference, around 2 or so, we call that ionic. And we would say in that case, the electrons are actually transferred. And you have a positive ion, cation, and a negative ion, an anion, that are hanging out around each other because they're positive and negative. And then if you have something in the middle, you have this polar covalent situation where the electrons are shared unequally, and you've got a partial positive on one side and a partial negative on the other side. All right, so let's try it. Let's look at some different bonds and make a guess as to whether you think the bond would be covalent, purely covalent, nonpolar covalent, polar covalent, or ionic. Yeah.
Where does this kind of show up in the field of chemistry? Where is this an important subject?
Good question. We'll do that in a minute. It turns out that this highly emphasizes the physical properties of a material. So whether it would be a high boiling point or a low boiling point, whether it would be very my brain is not thinking of a word right now. Volatile, whether it would be very volatile or whether it would not be volatile, whether it's a fume type thing. It also influences things like melting points, reactivities. If you go on and take organic chemistry, which for some of the health careers you may need to do that, this is going to be everything. All of organic chemistry pretty much can be explained by these kinds of interactions, positives and negatives interacting. So you need to know how those electrons are split up. So it's a pretty good, pretty foundational, important idea. In fact, and we'll get into this when we talk about vitamins, but the guy who published a big paper on all this is named Linus Pauling. I don't know if you've ever heard of him. He was a very famous scientist back in the 20th century, early 20th century, and he kind of came up with all this stuff in a paper when he was very young, ended up winning a Nobel Prize for it, and we still obviously talk about it today because it's such a foundational part of chemistry. He also ended up kind of going crazy when he got older and coming up with some truly ridiculous stuff, so it's kind of a fun story. And we'll get into that when we talk about that stuff in a little bit. But let's look at some examples of how we can look at some different bonds and decide how this interaction would look. All right, so here are some different bonds. These aren't molecules. They would have to have some more stuff to actually be full molecules. But just these individual bonds. And we want to know, how do we classify this? Is it more ionic? Is it more covalent? Is it something in the middle? Is it polar covalent? So what do you think between O and K, oxygen and potassium? How would you classify that kind of an interaction? Yeah, why?
Because the difference is...
Yeah, the difference is pretty great, right? 0.8 to 3.5 is a pretty big difference. So that falls definitely in the ionic category. Remember how in the last chapter, when we talked about naming, or I guess the same chapter, but the last part of it, we talked about naming and we said to find ionic compounds, look for the metals. And if it's metal, non-metal, it's probably ionic. Well, here's the reason for that. If it's metal, non-metal, chances are that electronegativity difference is so great that it becomes more like an ionic interaction. And there are exceptions to that. There are lots of things that look in one category on this little chart, but actually when you test it, have the opposite behavior, but we won't get into that right now. So our difference in electronegativity is about 2.7 for this one, so that puts it strongly in the ionic category, which means really an interaction between potassium and oxygen would not be a line. There would be no sharing of electrons here. A better way to draw that would be to say that this is oxide and potassium ions together. What about between arsenic and chlorine? Where would you categorize that one? Bipolar covalent? Yeah, the difference in electronegativity is about 1, right? 2.0 to 3.0. So that would put it squarely in that middle polar covalent range. Let's also look at that one. Could you figure that out without knowing the numbers? Could you make a guess on that without knowing the numbers? So look at this periodic table on the wall instead. Find arsenic, which is 33, and then chlorine, which is 17. We could say between those two, chlorine is 2 to the right and 1 up from arsenic. So we would expect chlorine to have a higher electronegativity than arsenic, and therefore we would expect this bond to be polar. So even if we didn't have those numbers, we could make a pretty good guess that that was going to be a polar bond. All right. Well, what about NN? Yeah, anything where you've got the same element on both sides is going to be nonpolar because there can't be any electronegativity difference. So that's just straight 0. Nonpolar covalent. And PBr, where would you put that one? Polar, yeah, polar covalent there. And these numbers, this like 0, 0.4, 1.8, you don't have to know those numbers. I don't even really like those numbers very much. It's kind of an arbitrary cutoff. It's like somebody just decided, well, if we look at most of the ones and how they fit, this is a good place to put those categories. But really, it's a whole range. And anything that's kind of right around that 0.4 or right around that 1.8, you're going to have to make a judgment on. It's not, there's no magic number that you can just say, aha, this is in this bucket. We have to test it chemically, see how it behaves. Does it behave more like an ion or a covalent compound? Anybody know how we would test that? How could you test if something was ionic or covalent? What do you think? Have you thought about this? How can you tell if something is made of ions or not? No ideas? There's got to be something, right? You could ask it.
If it's magnetic.
Magnetic? That could be. You could, but you're thinking about kind of in the right way that the magnet can attract ions in different ways. But also magnetism is a kind of a different effect, so you could be confounding it with that. But I like kind of getting into that realm. What else might be in that realm that you could do? Have you ever thought about this stuff? Electrical currents is how you would test this. Did you ever try to pass an electrical current through water? It's a little dangerous, so we probably shouldn't do that. But pure deionized water will not conduct much electricity because there's no ions in there. But if you have salt water, for instance, that will conduct electricity because of the sodium and chloride ions. So charged particles can conduct that electricity. And that's how we would test for ionic behavior, assuming something is that you could measure it either as a solid or in solution. If it conducts electricity in solution, you can assume it's making ions in solution. If it doesn't, then it's probably covalent. So that's kind of how we test it. And we can look at a plot of how this number compares with how it actually tests when you try to pass electrical current through it and see how well these numbers work out for you. So another way you can think about that. All right, so let's get into the physical properties. Let's get into why it's important to know these things about this electronegativity. So just as we, just as we looked at the polarity of bonds, we can look at the polarity of whole molecules also. Let's take water, for instance. Anybody know what the shape of a water molecule is? Like draw it in the air. Is it like straight across? Is it kind of bent? Is it in a circle? Do we know? No? Okay. It's bent. So it looks like this. It's made out of two hydrogens and an oxygen, kind of at an angle to each other like that. And the oxygen has two non-bonding pairs of electrons. So that bent molecule can have an overall polarity. That is, an overall, in a water molecule, can have an overall positive side and an overall negative side. But to do that, we have to figure out how its bonds are first. So if we look at each individual bond, would you expect an OH bond to have to be polar? Another way we say that is have a dipole moment. It's like the official measurement version of it. Would you expect an OH bond to be polar? What do you think? If you had to guess, we can go back and check. We'll go back and check that table in a minute. But if you had to guess, would you expect it to be polar? No? Who else? Who would not expect it to be polar? Who would expect it to be polar? All right. So let's look back up at the chart and check. The hydrogen's here. They move it over a little bit because it's not really a metal, even though it kind of goes over there. It really fits more with the nonmetals. So you got oxygen at 3.5 and hydrogen at 2.1. So is that polar? That is. That's a pretty big difference. And the way we could tell that is by seeing that hydrogen is well to the left of oxygen. So even though it's in a different row, it's well to the left, and so we would expect oxygen to be more electronegative.
So when would it be ionic?
Ionic is if that difference is greater than about 1.8. So usually that's going to be one of the metals and one of the nonmetals together. So each individual hydrogen-oxygen bond in this water molecule has its own little polarity. It's going to be a little bit positive on the hydrogen and a little bit negative on the oxygen. And same thing over on this side. A little bit positive on the hydrogen, a little bit negative on the oxygen. And those are two individually polar bonds. Another way that we sometimes express that is an arrow with a little plus on its tail. The little plus means that that side is plus, and the arrow points toward where the electrons are going, toward the more electronegative atom. So that's a way of expressing the polarity of each of those bonds. Now, if we want to know the polarity of the overall molecule, we have to ask ourselves, is there a way that we can kind of cut this molecule and have a positive side and a negative side? And in this case, there is. If you imagine kind of dividing the water molecule like this, everything below that is kind of more positive, and everything above that is more negative. You see how that would work? Because the oxygen would be above that line. So when we see a water molecule, which is really, in 3 dimensions, would really look something like this, because these atoms are approximately spheres. That's HHO. That's called a space-filling model of how these spheres kind of mash together. We would see kind of a negative area around this oxygen up here, and then a positive area around the hydrogens down here. And that separation says that the overall polarity of this molecule kind of goes like this. And we would call that a polar molecule. Another way we say that is that this molecule has a dipole or a dipole moment. Dipole is really a more correct term because being polar means you have 2 poles, so you're really dipolar, but we use it to mean the same thing. Now, to be able to evaluate this for different molecules, we need to know the shapes of the molecules. And there's a section in your book that talks about how to come up with the shapes of molecules, section 6.7. We're going to skip that chapter here because we didn't really talk about building these structures, and so it's not really going to be a part of what we do. But if given the shape of a molecule, we should be able to figure out whether that molecule is, on the whole, going to be polar or not. and see how that influences its physical properties. So let's take another one, carbon dioxide. Here's the structure of carbon dioxide. Carbon dioxide has two double bonds between carbon and oxygen. And the double bond doesn't affect the polarity. I mean, it does in that it's a slightly different length, but we don't need to think about that. We still look at the electronegativity difference to figure out the polarity. So do you expect there to be a significant electronegativity difference between carbon and oxygen? If you look at the periodic table. Is one of them more to the right of the other or above the other? It's more to the right. So we can probably say, yeah, oxygen and carbon, that should be a polar bond. That would be our guess. Let's go back and check our numbers. So the difference between carbon and oxygen is about 1, 2.5 to 3.5. So yeah, definitely that's a polar bond. So that means that we can draw those little delta pluses and delta minuses on oxygen and carbon. So which one goes where? Who gets the delta plus and who gets the delta minus? Right, carbon's less electronegative, so that's going to get the plus, and this one's going to get the minus. And we'd have to do that for all the bonds in the molecule. So let's draw our arrows also. On this side, we have an arrow like this. On this side, we have an arrow like this. So does that molecule have an overall polarity to it? Is there a positive side and a negative side? It kind of looks like it, but actually there isn't, because the positive part is in the middle. So there really isn't a positive side and a negative side. In fact, those two bonds cancel each other out. You can think of one as kind of pulling one way, and then one is kind of pulling the other way, and they end up canceling each other out. So we would say that, yes, each bond is polar. So this is a polar bond. Oops. But there is no net dipole. Net meaning overall. When we add everything together, they cancel each other out. And so there's no overall dipole. And the key to finding this in a molecule is to look for that symmetry. A highly symmetric molecule is going to have all its individual polar bonds cancel each other out. And so if we look at the whole thing, it's going to end up being 0. And that's what we see here. You got the same thing going on both sides. They cancel each other out. That would also be true for a more triangular molecule. So let me show you a couple different examples. We're going to look at two similar molecules, SO2 and SO3. So SO2 looks like this. And SO3 looks like this. There's a couple different ways to draw this, but we'll do it like this. Now, they're made of the same kind of bonds, right? They're both made of SO bonds. And would you expect an SO bond to be polar? Probably, right? Because one's right above the other. How would you draw the positive and negative, the deltas for an SO bond? Yeah. So O will have the negative and S will have the positive. in all those cases. So what would you say about the overall molecules in these cases being polar or nonpolar? Is one of them polar? Are both of them polar? Are they both nonpolar? What do you think? For the overall molecules.
SO2 is polar and SO3 is not.
How do you figure?
That's because of the symmetry.
Yeah, exactly. So SO2 is polar and SO3 is not polar. And it's because of this same idea. SO2 we can kind of cut like that. And everything below that line is negative and everything above that line is positive. So it's got like a negative side and a positive side. We can't do that with SO3. There's everywhere we draw, we're going to cut through a negative and a positive. And we're not going to have a negative side and a positive side. So that means that our SO2 is going to be polar, have a net dipole. And our SO3 is nonpolar, even though they're both made of the same kinds of bonds. They're both made of SO bonds, but one's polar and one's nonpolar because of the shape. Sound good? All right, so let's think about how this then helps us to talk about what happens when molecules get together with each other. And this is a really important part of chemistry because it really is predictive in that it helps us to explain things and it helps us to predict what we're going to find. This all goes under this heading of intermolecular forces. Have you heard of these two different prefixes, inter versus intra? Are you familiar with those at all? If you say that something is intra, what do you mean?
It's like in the middle of the process.
Yeah, it's like inside. And inter usually means between different things or among different things. So if we had a inter-classroom fight, we would all be getting up and fighting people next door. If we had an intra-classroom fight, we would all be fighting each other in here. Let's not do either of those, because I don't know about you, but I'm pretty weak and I probably wouldn't do very well. So it's the same thing with molecules. Intermolecular forces are the forces between different molecules. Intramolecular forces are the forces inside the molecule, which we call bonds. So we can probably make a little aside here. Intramolecular forces are bonds. That's what we call covalent or ionic bonds. Those are the forces between or among atoms in the same molecule. So now we're going to focus on what happens when different molecules get together. All right. There's basically two types of forces that we're going to look at: polar forces and nonpolar forces. So that's where this comes in of what we've just been talking about. We have to figure out if our molecules are polar or not, so we can figure out what type of intermolecular forces they have. So first we're going to look at the polar forces. These are stronger. And there's two types. First, we're going to look at dipole-dipole forces. What do you think that means? The book calls them dipole-dipole attractions. What do you think that might refer to?
That the negative and positive side attract each other.
Yeah, that molecules that have this negative and positive side end up attracting each other. So if we take our SO2 molecule, and I'm not going to bother drawing all the electrons in, you can go back and see that they're there. We said that this SO2 molecule had kind of a negative side down here and a positive side up here. So that means that that molecule can align with other SO2 molecules so that the positive and negative attract each other. So that looks like this. Or I'll leave that there. We'll draw some more. So the S and the O of this one, maybe the O and the S kind of go like this from another one. We know that this is a negative part down here, and this is a positive part up here. And we know positive and negative attract. So the positive and negative parts of each molecule kind of get together and hold each other together. And this could keep going. You can draw this now. The actual direction and shape in which they get in with each other could vary from molecule to molecule. I'm just guessing. I'm just kind of throwing something out there. Another way to do it, if they don't kind of fit directly like this, is you could kind of imagine them going like this. H-O, O. And like the partial negative. Hold on, I did that wrong. Negative. There we go. And the partial negative from the oxygen could go with the partial positive of a different sulfur. And so you could imagine these things kind of forming this big network all throughout. And that's how liquids and solids are formed, that these molecules get together and they kind of hang on to one another. All right. These happen in all polar molecules. And since they're fairly strong, that means that polar molecules are generally going to be held together more strongly than nonpolar molecules. All right, now we're going to look at a special subset of these forces called hydrogen bonding. And this is a terrible, confusing term because it sounds like it's referring to hydrogen bonding to something, because that's what the word is. That's actually not what it means. It's actually a type of the same force where one of the things is hydrogen. So hydrogen bonding is the same as a dipole-dipole force, except we only get it when our molecules are made up of NH, OH, or FH bonds. So when there are NH, OH, or FH bonds, we can get this special kind of force called hydrogen bonding. And the thing that's special about it is that it is extra strong. It looks the same. We can draw it the same way. So like with water, we still have a partial negative on oxygen, a partial positive on hydrogen. And that connects to another water molecule. And so on. And all these water molecules end up kind of linking up and forming this big structure. In solid form, we call that ice. In liquid form, we call that water. But it's a very strong interaction. That's why water's boiling point is quite high. Something like sulfur dioxide, even though it's polar, it still is a gas at room temperature, for instance. But water's forces with these hydrogens are so much stronger that water becomes a liquid at room temperature. Now, when we boil something, when we boil a liquid, these are the forces, these little red dots, that's what we're breaking. We're not breaking up the individual molecules. We're not tearing the O and H apart. The molecule stays the same in the vapor, but the molecules are separated from each other. So all that energy we have to put into water to get it to boil, 540 calories per gram, that's that heat of vaporization, that's the energy it takes to break apart these intermolecular forces, these hydrogen bonds. So if we know what types of forces, what types of interactions are going on in between molecules, we can have a pretty good idea of whether that substance will have a high boiling point or a low boiling point. And that's why this is so important. Yeah.
Would it be possible to break the bonds between O and H?
Sure. You just need a whole lot more energy. And that's called electrolysis. You can pass a strong electric current through water, and you can turn it into hydrogen gas and oxygen gas. That'll be a good one that we could do in class. We can check that out. Okay, let's look at the other extreme. The other extreme is the nonpolar forces. Nonpolar forces are a little weird. So I'm going to pull a picture from the book to kind of explain it so I can maybe draw it properly. It's on page 197. So if you don't have these dipoles, you don't have these partial positive, partial negative things, how do these molecules hold each other together? Good example of this are hydrocarbons. Do you know what hydrocarbons are? They're molecules made up of hydrogen and carbon. That's actually a good name. So it's actually a fitting name for them. But hydrocarbons are nonpolar because the difference in electronegativity between carbon and hydrogen is very small. They actually go into the nonpolar category. So what do we see as do you know any hydrocarbons personally? Are they your friends? You probably use a lot of them. You don't know about it, but gasoline is a good example. Gasoline is a hydrocarbon. It's made of mostly octane, which has 8 carbon atoms and 18 hydrogen atoms. Is gasoline a liquid or a gas? Liquid, right? So gasoline must have something holding those molecules together, even though they're not polar. So they don't have these dipole forces, but yet gasoline's still a liquid, so they must hold each other together. Have you ever seen wax, like in a candle? That's hydrocarbon too. That's nonpolar, but it's actually a solid. So something is holding that stuff together. Something is holding those molecules together, even though there's no separation of positive and negative. And the thing that holds it together is called an induced or temporary dipole. Make this bigger. So here's how that works. Here's our nucleus in the middle of 2 different atoms, 2 different nonpolar atoms. And here are the electrons. Now the electrons can kind of go wherever they want. Remember we talked about kind of a cloud of electrons around the nucleus? Those electrons can go wherever they want in that cloud. Sometimes those electrons are distributed evenly around the nucleus, and sometimes they're kind of lopsided. And we're talking like instantaneously they're lopsided because they're moving so fast. So at those instants that they're lopsided, there is an instantaneous dipole. So like if your electrons just happen to be over on one side for a tiny, tiny fraction of a second, there's going to be a dipole for that tiny, tiny fraction of a second. When that happens, it actually influences other molecules around it to do the same thing. Because as soon as you make a little bit of a dipole, whatever's right next to there sees that positive, and so the electrons rush over there to become negative because the negatives want to go to the positive. And then the next molecule over, their electrons rush over, and the next molecule over, their electrons rush over. And suddenly, you've created this kind of temporary dipole that all holds itself together just because everything still wants to keep it that way. And that's what we call dispersion forces, which are these very weak forces that hold these molecules together. Very weak in comparison to the ones we just talked about. Now, if the molecule is big enough, these forces can be substantial. But similarly sized molecules will always hold together stronger with polar forces than with nonpolar forces. Gasoline has around the same boiling point as water, a little higher, but it's got 8 carbon atoms and 18 hydrogen atoms in it, in each molecule, whereas water just has 1 oxygen and 2 hydrogens. So you need that many carbons to get these forces to be strong enough to just equal what one small molecule like water can do. And that's why these forces are much weaker. All right, so to review that, or to kind of sum that up, let's look at a little table again from the book of some of these different kinds of attractions and how they affect something like melting point. Oh, I didn't like that. All right, so here's some melting points of some substances and grouped by the type of interaction. So first we have the ionic bonds. This is a positive ion and a negative ion. And those are the strongest of all because those are full charges. So look at the melting points on those things. It takes a lot of energy to melt sodium chloride. You got to get up to 801 degrees C. That's pretty hot. Then the next strongest are the hydrogen bonds, which are way less strong than the ions. And then you got like water and ammonia, and you see where their melting points are. Then you've got ones that are not hydrogen bonding, but still dipoles, HBr and HCl, goes down even more. And then ones that are purely nonpolar, Cl2 or F2, that have no dipole at all, their melting points are the lowest of all, super low, because they just don't have those strong attractions to each other. All right, so let's try this. Let's see how this might work in practice. I'm going to draw some molecules for you, and I want you to try to decide if these would be polar or nonpolar, and then rank them in terms of their melting points or boiling points. All right, let's try this. And I'll probably want to put that electronegativity table back on here. We'll see. This one we don't really talk about. Carbon makes a structure called a tetrahedron, which is a 3-dimensional type structure, kind of pyramidal. It looks something like this. I don't know if you've ever seen a tetrahedron, but it looks something like this. It's a regular solid with 4 sides, 4 angles. And if you imagine the carbon right in the middle of that and the stuff attached to it on all the points, that's what that shape is. And the other one we're going to look at is again, that's that tetrahedral shape. That's not square. It's not straight across like that. So between these 3 molecules, first of all, which ones are polar and which ones are nonpolar? Let's here we can just grab our chart again here to help us out. If I can find it. So would you call HI polar? Why? There's a difference in electronegativity, but actually it's a really small difference. If we look up at that other chart here, this one says that 0.4 is about the cutoff for saying polar versus nonpolar. So HI is probably mostly nonpolar, maybe polar. Again, it's a judgment call, so we have to kind of say, what do we think? But it's definitely on the borderline. So if it is polar, it's not very strong, super weakly polar. Okay, what about these two molecules with carbon and fluorine? What's different in those two?
Well, the one has hydrogen, so it has a positive point and a negative because with the fluorine is the most negatively charged one. Mm-hmm. So all the electrons should move down there.
Yeah, so the difference between these two, now carbon and hydrogen doesn't have a big enough difference in electronegativity, so that doesn't really count. But carbon and fluorine certainly does. 2.5 to 4.0, that's a really strongly polar bond. The one in the middle here, the CF3, clearly has that separation because all the fluorine is down here at the bottom, which means this part up here is all going to be positive. And so that's going to give us a nice dipole, a nice polarity, a positive side and a negative side. And so what kind of forces would you expect that to have? Of those three we talked about, dipole forces, hydrogen bonding, or dispersion forces? Yeah, this is going to have the dipole forces. It actually also has dispersion forces because everything has dispersion forces. But the dipole forces are much stronger, so those will dominate. And what about the molecule on the right, the CF4? Will that also have those dipole forces? It won't, because in this case it's now symmetric. All the fluorines are all around the carbon, and there's no longer a positive side and a negative side. So it sort of like protects it. And there's no, so this one's really only going to show the dispersion forces. So you would expect those molecules, the CF3H molecules, to be able to attract each other more strongly in that case. There's some other things going on also, so that's not the whole story, but for our purposes, that's a good approximation. Now the HI is kind of a tricky case because we think, well, it's probably mostly nonpolar. If it does have dipole interactions, they're not going to be very strong. It's also relatively heavy though, so we'd want to look this up, kind of get a good sense of what the melting points and boiling points are. So it's helpful to help us understand what's going on in these molecules. Doesn't mean we can always answer all the questions. We still have to do experiments. We still have to measure these things and figure out what their properties are. But sometimes we can get a good idea about it by looking at the structures and trying to figure out what's going on. So does that work for you, I think? All right. All right, that pretty much takes us through chapter 6 now. So any questions about any of this stuff? Yeah. So when you go through chapter 6, the rest of it that you didn't go through yet, just skip the part on the molecular shapes because we're not going to get into that. But other than that, it should be good. Again, just follow the objectives in the homework on Blackboard and try to write through that stuff. Next week, we're going to get into chapter 7, which is a good chapter, sometimes a trouble spot for people. So you may want to read ahead a little bit on that. It's writing chemical equations and then doing some calculations about amounts of chemicals that you'd need to do a chemical reaction. So important chapter, sometimes a little bit troublesome. You might want to take a look at that if you haven't yet. And we should be able to go over the exams on Tuesday.
Do we have a quiz on Tuesday?
No, we won't have a quiz on Tuesday. We'll probably do it the next week. Otherwise, we got a little time if you got questions. Or yeah.
Do you have the exams written?
No. Sorry. I'll get to them as soon as I can. My other class took it last night, so I've got like, I don't know, 100 exams or something to grade between my couple classes. So I'll get them done. Not right now. Do you want to talk about some more stuff? Just call it a day? Okay. Everybody seems pretty you're not totally like destroyed by the exam, so that's good. There's still like smiles. Usually after exam, at least a couple people are just like glaring at you the whole time. Maybe after you get it back on Tuesday. Hopefully not. Maybe they'll all just be really good scores. I don't have to worry about it. Yeah, I've always had cool stuff. I don't know. Do you want to hear the vitamin story? Doesn't take that long. All right, let me find this guy. I'll tell you the vitamin story now, because this actually does. That's the guy. Oh. Kind of a crazy looking guy. So it actually does apply to what we're talking about, because it's intermolecular forces and all. Have you heard of fat soluble versus water soluble vitamins?
Yeah.
What are the fat soluble vitamins? A, E, and D are fat soluble. And the reason they are is because they are mostly carbon and hydrogen, therefore nonpolar, which is what fats also are. Whereas the water soluble vitamins are mostly O and H and N, and that's the kind of stuff that is polar and can get into your bloodstream or can dissolve in water. So your fat soluble vitamins can accumulate in your body. Well, anyway, so this guy, he comes up with all these great discoveries in the 30s, electronegativity, polarity, all this stuff. Then he kind of moves and goes into molecular biology, makes some interesting discoveries about structures of proteins, does some preliminary work that ends up influencing the structure of DNA, all this great stuff. Really like brilliant stuff that everybody knows and is highly, highly respected, probably the most famous scientist in the world. He goes on after World War II to work on nuclear disarmament and peace treaties around the world, and is a key figure in that, and ends up getting a second Nobel Peace Prize, a second Nobel Prize in Peace for his work on nuclear disarmament. So by this time, he's just the greatest guy ever, super highly respected, and this is like 60s-ish. So into the 70s, he's getting a little older, and he somehow decides that vitamins are the cure to everything. That if we just had enough vitamins, if people aren't taking enough vitamins, if we just took more vitamins, we wouldn't have, first you'd say colds and flu, that would be eliminated if we just took huge doses of vitamin C. Have you heard this?
Yeah.
You take vitamin C for your colds and your flus, right? And then, of course, he's this big famous scientist, so people basically said, all right, great, let's start taking vitamin C. This huge vitamin supplement industry starts becoming a thing based on a lot of what he says, and people start taking huge doses of vitamin C. People start saying, oh, I got a cold, I got to take my orange juice, I got to make sure to get my vitamin C. The problem is that while he's saying all this, scientists are actually doing the work in the lab and trying to prove this, trying to show this. And they keep seeing that it doesn't work, that it doesn't matter how much vitamin C you take, it doesn't help you in any way. It doesn't help you get better, doesn't cure your cold, doesn't cure your flu. Sure, you need enough vitamin C so you don't get scurvy, but it doesn't like magically cure you. So he starts to get a little heat from the scientific community about this, but it doesn't faze him at all. And he actually extends it and says, well, not only that, but we should be taking tons of vitamin A, we should be taking tons of vitamin E, and it's not going to just cure our colds and flus, but it's going to stop cancer. And he famously said in a big article in a major magazine that within 20 years, cancer will be eradicated in the world once people start taking enough vitamins. So, of course, famous, great scientist starts, people listen to him. I mean, especially back in those days, he would go on these lecture tours and it was like a concert. Like people would sell out these huge venues to come watch him speak, and like he'd go on all these shows and in these papers, and people would basically believe what he said, even though at that point there was no longer any actual science behind what he was saying. So it was a big problem, and it ended up kind of being a sad thing for him, because not only did he, not only were these megadoses of vitamins not doing anything, but evidence started to surface that they were actually doing harm. That if you take vitamin A, vitamin E, specifically supplements, that you're actually at a higher risk for many types of cancer and heart disease. And that just in the last 10 or 20 years has become really, really clear, to the point where they had to stop some major studies because it was so obvious that the people taking supplements, taking supplemental multivitamins, were having negative effects. So don't take vitamins is the answer to that. You don't need a multivitamin unless your diet is so bad or is restricted for some reason that you are not getting those certain types of vitamins. And he ended up dying of cancer.
When he said these things, did he maybe have like a business contract with a supplement company?
He didn't actually at first. So there's a lot of thought about like where did this come from. He saw some talks from some kind of quack scientists, like fake scientists, talking about this, and he was really taken by them. So we don't really know. It wasn't kind of like a cynical business thing. He just decided one day that was the truth, and he was going to start pushing for it. It was a hypothesis that he had in it, and at that point in his life, he just wouldn't listen to this scientific information anymore. So yeah, and that happened, and then now he's actually mostly known, or he's probably most famous for his work on vitamins. He's always associated with vitamin C and all this stuff, even though the actual good science he did was really important, and this stuff was all ended up being all nonsense. So, and his legacy still goes on to this day. You go into a drugstore and it says, you know, vitamin C drops for your cold, vitamin C this for your immune system, and none of that's ever been shown to work in any way. So that's the story.
He ended up dying of cancer.
Yeah, he ended up dying of cancer. So don't take your vitamins. All right.